In the last clip, we concluded the lecture with asking ourselves the question, why engines have become so big? And that's what we'll have a look at in this video clip. So we saw this development from relatively small engines to very large engines in which a part of the air doesn't even pass through the combustion chamber. Why this development? Well, the technical word for this development is what we call it's a higher bypass ratio. So the bypass ratio is the ratio between the cold air that passes by the actual jet engine divided by the core airflow, or the hot air. So the m dot C stands for cold, m dot H stands for hot, and this bypass ratio is not a fraction of 1, but much larger than 1. And it results in an air which has a lower speed when it leaves the engine. So we have more cold and less hot air, and we also have a lower speed. And we ask ourselves, why is this? Well, to understand this, we have to look again at the energy, at the power perspective. If we have a jet engine, we increase the speed of the air. So the air has a higher speed at the exhaust than at the intake. And the amount of energy which it has taken to increase the speed of the air, the amount of extra energy that's in the air, is simply the change of kinetic energy from the air when it enters and when it leaves the engine. We call this the jet power. So it's the amount of power that it takes to accelerate this jet. And that's, of course, if the engine is very efficient. There's also all kinds of effect of mechanical effects in the engine. But this is the net amount of energy that goes into the jet to accelerate it. The change of kinetic energy from the end minus what it already had when it entered the engine. Well, we know that this is not the same as our propulsive power. Our propulsion power, the power available for the propulsion, has a different equation which we derived earlier, and that's that it's the thrust times the speed. And we know that the thrust is generated by the mass flow times the speed difference. Well, this allows us to calculate the efficiency of generating propulsion with a jet. Simply by dividing the propulsive power, the available power, by the jet power, gives us the equation T times V0, T times V we sometimes call it. In this case we have also the exhaust speed, so we have to make the difference. So T times V0 divided by half m dot Vj squared minus V0 squared. Let's have a closer look at this equation of the jet efficiency. Because the thrust times V0 we can also replace by the equation which we have for the thrust. And if we fill m dot times the speed difference, if we replace t by it, we get this equation. It looks more complex, but look at what we can strike away here. We see the m dot both on the upside and lower side of this equation. Vj minus V0 we can take out, and the half divided by half is the same as multiplying by 2. So if we simplify this a bit further, we see that it's basically the same equation as 2 times V0 divided by the sum of the speeds. And if we then divide both parts of the fraction by V0, we get the equation 2 divided minus 1 plus the ratio of the jet speed divided by the intake speed. If we look at this equation a bit further, we see that we can calculate the efficiency, so the jet efficiency, only by knowing the two speeds, the jet speed and the exhaust speed and the intake speed. What does this mean for our efficiency? Well, we always strive, of course, for an efficiency of 100%. So it means that eta g, this expression, has to be 1 then. And that shows that is possible. If we have 2 on top, we just have to make sure that the denominator is also 2. And that means that 1 plus Vj divided by V0 has to be 2. So Vj has to be equal to V0. Then we have 100% efficiency. If we make the exhaust speed equal to the intake speed, we have 100% efficiency. Of course, the problem is that our thrust then becomes 0. So the good news is we have 100% efficiency. The bad news is we have 0 thrust. So we can generate 0 thrust with 100% efficiency. That's of course not new, we knew this. But look at the difference between the two equations. We see that the mass flow is only in the lower one. So we can still reduce Vj minus V0 and get the same amount of thrust as long as we increase the mass flow. And increasing the mass flow doesn't hurt the efficiency because the mass flow is not in that equation and it will lower the Vj. So this is an important trick to increase the efficiency of our jet, increasing the mass flow and then reducing the jet speed to get the same amount of thrust. And this is what has caused this development in engines, which we easily recognize. We can immediately see that this 737 is an old aircraft because of the small diameter of the engines here. And if we then look at a newer type of 737 in 1998, we immediately notice the larger engines here. Let's flip back one more. We see here smaller engines, and then 28 years later, we see the much larger engines. And this is because this is much more efficient, as we have seen from the previous derivation. More mass flow, lower exhaust speed because the air is mixed, but this generates a much higher propulsive efficiency. Well, there are more trends that we've seen. There's also seen that the engines have become much quieter. Well, much quieter engines is simply a result of a lower exhaust speed as well. The mixing of this high exhaust speed with the airspeed, this creates all kinds of turbulence, and that's one reason that the engine have become much quieter. And you see here the relation between the noise level on the y-axis and the bypass ratio on the x-axis. And see how this bypass ratio 5, 6, 7, 8, it has, and these are real numbers that you find today, has really reduced the noise level because the mixing of air is less turbulent and therefore it creates less noise. So often you will hear from engine manufacturers or aircraft manufacturers that they have increased or have made their engines more green, less noisy, more silent, and also less emission. But of course the main improvement from the airline perspective is that it uses way less fuel because it's much more efficient. In the past, you could only cross the Atlantic Ocean or the Pacific in an aircraft which had 3 or 4 engines. And nowadays, we often see aircraft with only 2 engines cross the Atlantic. There are still certain areas where you're not allowed to cross with 2 engines, but they have created rules which are called the ETOPS rules, extended twin operations. You see the joke here on the slide. Some say engines turning or passengers swimming. Because the idea is that due to the higher reliability of modern engines, it is possible to fly over the ocean because the chance that 2 engines failed on the previous aircraft is just as high as that 1 engine fails on this modern aircraft. So there's still a limitation. There are still certain areas where they can't go, but this ETOP rules is also an effect of the advances in engine technology. And what will the future of the engine developments bring? Well, as we have seen, the larger you make engines, the more efficient they become. So even bigger engines is a possibility. But another thing to note is that propellers are still more efficient in terms of propulsion than the jet engines. The advantage of the jet engines was the less mechanical wear and tear and the high speed, but it's possible to generate with modern technology the same advantages with turboprops. And when fuel efficiency and lower emissions get more and more important, we might see the return of more turboprops, perhaps with counter-rotating propellers or other forms of unducted fans or propellers which will be used again. Be aware that even though these aircrafts are greener in the sense that they have less emissions, they will also be noisier again. Some say, of course, that we should really strive for hypersonic travel, and then we might see the scramjets again. They are not very efficient, but the part that you travel outside of the atmosphere, of course, there's no drag Similarly to is the reason why we go to the stratosphere today, the thinner air, the lower drag. Some say that you gain some efficiency there, and that the advantages of being able to fly to Australia in only a few hours from Europe is an advantage which might be sufficient to introduce this hypersonic aircraft again. And then we need a scramjet, a supersonic combustion ramjet. And who knows, there might be more specializations. We have boundary layer ingestion types of engines, positioning of engines on top of the aircraft to use the aircraft as a noise shield. There are many specific developments tailored towards optimization of one kind, which might result in a different configuration of the aircraft, but also different types of engines. And who knows, maybe in the future we'll even have electrical engines on the large aircraft, but that we'll still have to see.